Okay, so we'll record this so people who couldn't come, like Kristen's not here today, so she can watch this and follow along. We'll try to do as much as we can on the board so she can see. And you guys can take some notes, but these notes that we take here, we can just post them online, print them off, whatever, so you'll have these to study from. All right. So I have a bunch of blank slides down here that I'll take some notes on too. We'll just work off of these. All right. First topic. We've got this is chapter 15, electric forces and electric fields. First of all, some fundamental ideas. All right. Can you close the door down there? So, big ideas here. We've got this stuff called charge. Another conservation principle. Charge is conserved, which means the total amount of charge you have in a defined system is going to stay the same. All right. Big idea. Second idea. There are two types of charges. We call them plus and minus, or plus and minus charges. All right. Third big idea, charge is quantized. Does anybody know what quantized means? There is a fundamental unit of charge. All right. You can divide them, like I can have 18 zillion charge units, and I can divide them in half and half and half. I'm going to get to a certain point, though, where I'm down to one charge, and I can't divide that charge in half. They're in quantum chunks, all right? So one charge, so charge is quantized. So they come in little packages that can't be subdivided. What else comes in tiny little packages that can't be subdivided, sort of? Well, let's start atomic particles first until they figured out how to divide them, right? So charge is quantized. So it's all right. And just like we can divide matter up into smaller chunks until we get down to the atoms, right? So this is sort of like atomic property. So in atoms we've got protons, we've got neutrons, and we've got electrons. Our little simple model of an atom. We've got a nucleus, and we've got this cloud of electrons around the atom. And so these are the fundamental building blocks of matter, as protons, neutrons, electrons. Until they figured out, and this is the early 1900s, they started subdividing these into what? We got quarks, bosons, leptons, and so you gluons, luons, yeah. So you've got all these subatomic particles, and this is what we call our modern. This is modern physics. All right, we're doing classical physics, which is everything before 1900, essentially. All right, after 1900, it's basically quantum physics, and what's a standard model of an atom now includes all these things. This is called the standard model. All the stuff underneath these things are built out of is called the standard model of an atom, and that's part of modern physics. And that's the last few chapters of our book. And this is not done in any of the AP Physics. I don't think any of them cover. Actually, AP Physics 2 covers some modern physics, I think. So the second follow-on course to this one covers, not from a calculus standpoint, but just some basic ideas behind it. This version doesn't, though. But the idea here is we get down to these fundamental particles. Well, and charge is related here, because where do these plus and minus charges come from? Well, the minus charge is from our electron. All right, so an electron has one of those fundamental units of charge. And our proton has another fundamental unit of charge. All right, so one proton carries that one positive charge. One electron carries that charge. And our units are what? Anybody know what the units for charge are? They're called coulombs. All right, named after the scientist Coulomb, who was involved back in the late 1870s in figuring this stuff out. So how many coulombs is in one charge? Anybody know? It's obvious, right? It's don't stop cheating here. Don't say anything. You're supposed to say one. You're supposed to say one, but no, it's not 1 coulomb. All right, 1 coulomb actually is a huge amount of charge. You'll see where 1 coulomb comes in later on. All right, so 1 electron equals negative 1.6 times 10 to the minus 19 coulombs. All right, 1 proton equals positive 1.6 times 10 to the minus 19th coulombs. All right, so a fundamental unit of charge, our smallest quantum bit that we can divide into, is that much from a magnitude standpoint. And we have a plus or minus sign, which indicates that we've got a proton or an electron.
From a dimensional analysis standpoint, what is a coulomb?
Those are SI units, first of all. All right, that's a little bit trickier question to answer. All right, so let's just stick with coulombs for now. All right, you'll be able to see later. I'll get a better idea of the units when we start using these. All right, so we've got these coulombs. Okay, so we've got so charge is conserved. We've got these things that are charges. We have positive and negative charges. Charges quantized. We know that negative charges are going to repel, so they're going to repel, all right, and opposite charges, these are going to attract, and we can take two positive charges here, and they're going to repel. So like charges repel, and unlike charges attract, all right. All right, so those are some key initial ideas. And now if we have our object, for example, we have our little rubber or latex balloon here. A latex balloon is made up of a whole bunch of atoms, right? I mean, there's not a mole of atoms in a balloon. That's a fraction of a mole. Moles, I don't know, that's quantity, I don't know, a liter of something, roughly speaking, is a mole. You guys know how to do molar calculation, stuff like that. So you should know, roughly speaking, how big a mole of something is. So that's less than a mole of latex, I would say, in there, whatever compound that is. But still, that's a lot of atoms, right? Because 1 mole is how many atoms? 6.022 times 10 to the 23rd. All right, that's Avogadro's number. So there's a whole bunch of atoms in there, all right? And each one of these atoms is comprised of protons, neutrons, and electrons. And as a whole, any object should have, roughly speaking, an equal number of these things. And when I have a plus charge together with a negative charge nearby, as a whole, if you draw a circle around it, our total charge equals what? Our total weight equals 0 charge. They'd cancel each other out. So we can add together our charges to see what our total value is. All right? So there's so many positives, so many negatives, and if we have equals of both, then our total charge on an object is going to be a net of 0, because positive and negatives will add together and cancel out. Okay, so let's talk about. So we've got an object now. Let me ask you, how about a rubber balloon? So say we have a rubber balloon. And you guys know about whether something is an insulator or a conductor, right? You guys from, I don't know, 3rd, 4th, 5th grade or whatever. Is a balloon an insulator, a good insulator, or a good conductor? Good insulator, it says, right? So it can't conduct electricity at all. Not well, all right? So the charges can't move freely, all right? Versus if I had a metal sphere, and everybody would probably agree that a balloon is probably a good insulator. What's the difference between the two from a chemistry standpoint? Nothing to do with density. It's a material property. There's something about the atomic structure that will dictate whether or not it's a good conductor or an insulator. By the way, there's something in between. It's called a semiconductor.
Are ionic bonds in conductors?
Well, yeah, it's all about the bonding and what you have on your outermost electron shells. Water, a good conductor or not? I would say water, electricity can't, but it's not. I wouldn't say it's a great conductor. Better than rubber, probably. How about a ceramic cup? That people would consider a really good insulator. All right, both from thermal properties as well as electrical properties. Very difficult to get. In fact, if you go back to the old days where you have old fuses in house, anybody have the old fuses you screw in? There's a ceramic base and a copper, like a light bulb base type of thing, but it's ceramic in the middle of the glass housing and then a little conductive element in between. If you put too much current through it, it burns up. We'll talk about that when we get to resistance. But the ceramic is great because it's not gonna conduct electricity, so it won't short through there very easily, and you won't get electrocuted. If you think about, let's just take these objects. Say, all right, now we've got these objects. We call one an insulator. We call one a conductor. There is something in between that's sort of conductive. If you force it a certain way, it'll become conductive. If you force another way, it won't be conductive, and that's what we call semiconductors. And what materials are examples of semiconductors? Silicon, gallium arsenide. Those are the two most common ones we use in the semiconductor insertion. Those are our electronics are made out of. The properties of semiconductors are really important. We won't go into a lot of detail about those. But if I had any of these objects, a balloon, like a balloon or a hunk of silicon or gallium arsenide or a hunk of metal, I mean, generally speaking, I'm going to have, however many atoms, right? And atoms, of course, generally speaking, have an equal number of protons and electrons. You have your protons in the nucleus and your electrons in the shell around it, and then there'll be, if you have multiples of these things next to each other, they're interacting with each other with different types of bonding. So on a balloon, I don't know, I'll draw, like maybe we have, like in all these objects, maybe we have 6 charge units that are positive, and we would have maybe 6 that are negative, all right? And it's the same for these other things. And I'll just show that, in a balance, in a general situation, things are in balance. All right, so we have balanced number of charges on these objects. So they're neutral. We'd call that neutral. Okay? So we're going to have a balance here. All right? Now, what I did to start is I actually took the balloon and I rubbed it on my hair. All right? So we can actually cause an imbalance in charge. By rubbing things together, we can actually take charge from one object and transfer it to another. And it turns out certain objects and certain materials have certain properties. Some things like to give away their electrons. Some things like to take electrons. And those things, you could actually look up on the list, and I'd ask you to go through and do that. There's something called the triboelectric scale, and people back in the 1600s worked out this scale. This is when they really started to figure out things about static electricity and started to develop the whole concept of electricity back in the very end of the 1500s into the early 1600s. And we mentioned a guy in our lecture today who was talking, the guy who's doing magnetism was related to this as well. I can't remember if it was a G, the English guy. Triboelectric scale. And on this triboelectric scale, you'd have, basically, it's a list of different types of materials like balloons, like rubber. You have wool. You'd have glass. You'd have nylon. You'd have, what are the common things? Do they have? Fur, like rabbit fur, human hair, all these different things that carpet, for example, would fall under one of these categories. Because when you think of the times around the house when you have these static electric charges spilled, what's causing the charges? It's when you're scuffing along things and you're taking charge from one thing, and some things like to give up electrons, some things like to take them. And if you put two things at the opposite ends of the triboelectric scale, rub them against each other, one of them tends to let its electrons go, the other one is pulling them, and you take them apart, and all of a sudden one thing, although they're in balance to begin with, one of these materials, like a glass rod on a rabbit skin, which is why I have those rabbit skins up there, by the way. If I rub a glass rod on a rabbit skin, one of them, I can't remember which is on which end of the triboelectric scale, but one of them is going to want to give up its electron. The other one would like to take more, and it's because of what's left after the chemical bonding, the covalent bonding, how the orientation of these bonds are such that it's more likely to want the electrons based on the valence shells that are available, and which one is likely to give them away because and so on and so forth. All right. Question.
So it's always electrons being transferred.
In reality, yeah, because in reality your protons are part of the the nucleus, and your nucleus isn't what's going to move around. It's always going to be your electrons that are going to be transferred. However, what's the difference between transferring electrons, and how can I tell the difference between electrons moving versus protons? It looks like it's the same thing happening, but we know, in fact, there are positive charges associated with the atoms, and the atoms aren't actually moving themselves, but the electrons are. But whether it's the electrons that actually physically move or the protons that physically move, in essence, you get the same result. All right. So we still treat flow of charge as either positive charges moving or negative charges moving, even though in reality we know that it's the electrons that are moving. And one of the things to think of, if I just have a material where I have all my positive charges and I have my matching negative charges, and notice I left one blank here. So here I have a net positive charge of 1 here, and if I move this electron over to here, all right, now this electron is gone. It looks like I moved an electron over 1, or did it look like I moved my proton over 1, which happened. 6 and 1/2 dozen of the other in essence. All right. So whether we actually have the positive charge moving or not is sort of irrelevant. But we know in reality the electrons are the ones that tend to move and the protons are stationary. But you can visualize either of them as moving. Okay. So that's a good question. So look up the tribal electric scale on Wikipedia, and you'll see the list of materials. And if you pick things on opposite ends, so do this on Wikipedia, you can actually see the list of materials. And I have a whole box of those materials over there, and we can play with them. We can do that later on after the exams. We can go back through them and play with some of these things. Okay. So, what the balloon and my hair were on two opposite ends of the tribal electric scale. So when I rubbed it on my hair, either my hair was giving up electrons or the balloon was giving up electrons, and one or the other, and I don't recall which it is. I'd have to look up the scale. So that balloon was either had a net positive charge or net negative charge. Now with a balloon, we know a balloon, we said it's not a good conductor, right? So rubber, we would all agree. So we've got a rubber balloon. It's not a good conductor. And let's just pull up the tribal electric scale and let's just see what it was getting. So this guy, back in the 1750s, he sort of compiled a nice list. And, all right, so materials are often listed in polarity to charge separation when they are in touch with another object. So a material towards the bottom of this series, this tribal electric series we call it, is if it's touched near the top of the series, it will require a more negative charge. All right, and you see alongside here they actually show the series. So on the bottom of the series, now where's rubber? So you notice here's fur, leather, glass, nylon, hard rubber, resins, rubber balloon, and on the other side of the scale. So it's down in the middle of the scale. But the things lower on the scale will pull electrons from the things that are higher on the scale. And so that's going to mean so where's human hair? Oily skin is right up here. So our hair was giving up electrons to the balloon. So our balloon had extra electrons, and my head was left positively charged. So I have excess positive charges. So after I rubbed it on our hair then, this pulled excess, so I'll leave our... So let's say I rubbed my head against, let's say my head was over here, all right? So here's my head. All right, and when I rubbed this thing against my head, 1, 2, 3, 4, 5, 6. So basically, I gave up some electrons, because my hair easily gives up the electrons more easily than this does. Let's say I rubbed it on this side of the balloon. So I've got 3 extra charge quantities here. So I've got, on this side of the balloon, I just collected some more charge. Now, a balloon, is it a good conductor or not? And what's a conductor in? What happens to charges in a conductor? Electrons, typically what we're talking about. They can move through it really easily, right? Balloon, not so much. So on this side of the balloon, where I rubbed it against my head, those charges were pulled off of my hair onto the balloon. So my hair my head on the side that it was rubbed against has a net positive charge. All right, so I have an excess of positive charges over here. So my side of my head here is positively charged. This side of here is still neutral. And in the same sense, because my head's not a great conductor, so these charges won't redistribute. In the same sense, for this balloon, I have a net negative charge over here, and we're neutral over this side because we still have a balance of charges. All right. So if I were to stick this to the wall, and the question is why is it sticking to the wall? Apparently the wall likes these negative charges and it wants to pull them. So our wall has an attractive effect, so there must be some sort of electrostatic force acting between the two to hold it up against the wall when I were to plug it against the wall. So I could take this side and it'll pull towards the wall because the wall must want to take extra electric charges. Actually, if the wall is sort of grounded, the extra charges will want to go towards the ground to neutralize, because everything wants to be in balance. And so by putting this against the wall, it'll actually attract to the wall because it has an imbalance in charges and it'll pull on there. But let's get into the forces later. So by rubbing it against my hair, I've got one side of this balloon that's going to have a whole bunch of excess charges. The other side of the balloon won't be affected because these charges can't redistribute. All right. On the other hand, if I were to use, instead of a rubber balloon, something on our scale that was above that was a good conductor, these extra charges, well, I've got extra negative electrons right next to each other, and two electrons next to each other are going to want to do what? They're going to want to repel, right? So if I just show the net excess charge on this object, right now we have a net excess charge of we've got 3 extra on this side, and they're sort of stuck there if this is an insulator. All right. If this was a conductor, on the other hand, if I had 3 extra charges dumped on one side of it, 1, 2, 3, on a conductor, those things can move. All right. So these things would move on a conductor. All right. So they'd move away from each other, and they would redistribute. And so in the end, I would have a negative over here, I'd have a negative over here, and I'd have a negative over here. They'd be as far away as possible from each other. All right? And they would automatically redistribute if you could move in a conductor. On an insulator, you can't, so they're sort of stuck on one side. All right? So on this balloon, when I was charging it on one side, and I could still feel the interaction here. So this side is charged now. This side is not as much. So if I bring it over next to my device here, on one side it actually makes these little veins move. On the other side it has no effect because there's no imbalance of charge on this side. So you can see that happening here. All right. So, and I did that. So this is the side of charge. If I put this to the wall, on this side, it should stick to the wall, all right? Whereas on the other side, you see what it just did? The balloon just flipped over to the other side where the charge was strong. Because apparently this wall likes this excess charge and is trying to attract it towards it. So try that again, and just rolled over to the side that was charged, and it sticks there, all right? Until the charge disappears. Where would the charge disappear to? Because charge doesn't disappear, right? Where's the charge going to go to? To where? To the wall? Air, especially if there's moisture in the air. So on humid days, it's hard to do these electrostatic experiments. In the wintertime, it's good because your air is drier. But like using our Van de Graaff generator and stuff like that, it's best to do that in the winter time frame. You get much better. You can contain your charge and hold it much better, and then discharge it really easily. Whereas this, it bleeds into the air, and just it wicks off into the air basically. It's the water molecules are on the other side of the triboelectric scale, picking them up again. All right. Now, what would happen? Let me ask you this: what would happen then if I took this balloon, which has an excessive charge on one side. I'll just show the excessive charge. And what happens if I were to move it nearby? I've got my metal can here, all right, and I'm going to show 6 representative charges on my can. Okay, so there's my 6 representative charges on my can. If my can's just sitting here, and of course now I'm going to have to chug this thing. So this is like a soda can, an empty soda can. If I had it laying down on the side with no excess charges on it, and if I did have excess charges on the soda can, either positives or negatives, they'd sort of smooth each other out. If I had excess electrons, they'd just be evenly distributed throughout the can. Excess protons, they'd be evenly distributed. But let's just say it's equal to start with, and if I bring nearby it this balloon, which has a bunch of extra electrons on one side, what's going to happen as I move it near this can? What? I'm not going to touch it. So there's no touching. If there's no touching, I can't transfer the electrons, unless I can get an arc to go across. These electrons, because it's a conductor, and because these are all, remember what metals have. They have all these valence bands on the outer, they have a ton of valence bands at their outer valence bands that are filled with, that are nearly empty. And the electrons can float into those valence bands and move through the metal really easily. That's what makes it a conductor. So these electrons are free to move very easily. And if I bring an excess number of electrons over here, what's going to happen? These electrons on this side are going to want to run and get away from them. So as I bring these close, we've got repelling here going on, right? These are going to repel, and what will happen is these ones will flee over to the other side.
You were right.
And then what's going to happen?
You're going to go that way.
Well, no, all my negatives are over here. So now on the right side, I have a net charge imbalance of 3 negatives. On my left side, I have a net charge of what? 3 positives.
Will they attract?
And they should attract. You think that'll happen?
Wait, will it happen? Yeah. Yeah, that's okay, yeah.
Okay. Ready?
Look, it's moving. Wow, you two.
Here we go.
Oh, you're wrong.
And this is quite a strong effect, too.
Boy, something happened to all the negative ones on that side then?
So these have extra, let me flip this around.
None.
Nothing. All right.
As it spins, are the negative ones still like?
Oh, they just stay on the opposite side because they can flow freely in metal. So all the negatives, as many negatives as possible until you achieve a balance, are going to be over on the other side, which leaves a net positive on the side of this can. And now we got a positive negative interaction, and they'll pull together. All right. Now, all right. So and the total number of charge here is not changing. Remember, charge is always conserved. So we can draw a box around the system. All the charges are the same. Now, if I actually touch this to the can, what would happen, do you think? What would happen if I touch this to the can now? Yeah, I mean, I have excess on here, and I could transfer some to the can. I could actually feel it quick when I did that. So now, what should happen then if I bring these close to each other? Well, let me recharge here. Now I have a bunch of extra electrons on here, on this can as well.
Should they push? I'll keep them away.
Well, I have a bunch here, a bunch of electrons here, a bunch of electrons here. They can still move, so I should still be able to pull it, but I'm not getting nearly the force. I was trying to. Do I have anything stuck? I'm stuck on something here, maybe here.
There's more electrons?
I'm still getting a pretty good pull on it. But it depends on how far away these can move, I guess, as you say. But I'll still be able to get a pull on it because I can still, as many electrons they have in here, it's going to force the electrons over here. They're going to repel. They can move all they want on this can. Those are still moving to the other side. But I just have more on this other side of the can. And so if you look at the force involved with it, and what's causing the force? I have all the positive charges here attract the negative charges here. But I still have the negative charges over here, which are still being repelled on the opposite side of it. So it's still trying to push the can this way. And this is a 1 over r squared relationship, just like gravity. The ones on the far side, if they're twice the distance away, they're going to have only 1/4 of the effect on the force, and so they're going to have a minimal effect. So it'll have a slightly reduced effect on pulling the can, but not too much because they're probably enough distance away that 1/r² is going to reduce the impact of them doing that. So we do a little experiment, see if this is still hanging on the wall on Monday. All right, so that's a little bit about transferring charges. And if you read in the book, they talk about insulators, conductors, charging by induction. And so we have charging by conduction and charging by induction. So when I actually took that balloon and touched it to this can, that's called charging this can by conduction. I actually added charge to the can by actually physically touching and add an excess amount of charges on the balloon, and I transfer to the can. So you probably want to know some of these definitions since you want to flip to that. That's on 495. Induction is, if I were to use induction, what I could do. In fact, we could show this induction. All right. And you notice I got to touch this against this plate here. This is grounded into the ground, so I should be able to get rid of my excess charge on here. Okay, so if you watch this, I'm moving my vanes again on here, and they're moving apart. Now, if I touch this can to this, all right, I should see. Because what should happen is if I move my balloon close to the can, the electrons on this are free to move, and all my excess electrons will flow over to one side of the can, get away from me, all right? And then because it appears there's a whole bunch of excess of electrons, I could actually touch it to I could touch it to, let me see if I can do this. I'm going to touch it to ground over here. Problem is this is painted. I'm not sure how much of a good ground I'm going to get. Well, actually, we'll try it. This might work. Because what I can do is I can push away the electrons down to one side of this, and it'll appear as extra electrons, and those should flow into the ground, and it should leave this can positively charged, all right, without me touching the balloons to it. So let's just try to see if I can make this happen. So I'm just going to move that close. Now, yes, I'm looking at it. But if theoretically, I could actually bring this close, and this side will be more positively charged, this side will be more negatively charged, and it'll look like they're excess electrons, and so I could take these excess electrons, put a wire down the ground, and bleed them off into the ground, because the ground will take all those excess electrons and neutralize things. And then if I disconnected it, I would actually have excess protons left on here with less electrons, and this would be positively charged. That's what we call charging by induction, all right? And they have a nice diagram of that in the book on page 500. All right. Now, you saw, and you know this, right, from static electricity, things like to attract or repel. Yep.
So would ground always take electrons? Now, what charge does ground have? Is ground just like 5 electrons?
Well, ground's a whole bunch of atoms that have a whole bunch of protons and electrons, and so. We talk about electrons because they're the ones that tend to move. But if I have an object that has extra electrons, they'll go to ground because ground's like a big sink. But if I have an object that has a whole bunch of excess protons, it'll pull electrons out of the ground as well.
So it's like an infinite supply
of either, I guess.
Because there's a lot of imbalances, generally. So there's always going to be.
So Earth's a big balancing pool. Essentially. Okay. And Kristen, now I have pizza in my mouth. Okay.
All these experiments are great.
Now, we just saw, we hit a balloon, and then we hit a can, and there was certainly an attractive force between those two. And so we had a nice balloon here, and the balloon had a net negative charge, okay? And then we had our can, and we actually induced a charge difference in here, so we made all these negatives fluid, so we had a net negative over here, we'll set this net positive Q over here, some sort of charge imbalance that was positive Q. And then negative and positive, and we have an attractive force between the two. So let's just put. I'll just draw out the free body diagram. So we have force and an electric force here. How big is the electric force going to be over here? It's going to be the same. All right. This is Newton's third law. For every action, there's an equal and opposite reaction. All right. The question is, how big is that force? Well, what does this diagram look like? I've got an object here, an object here. They're separated through space, and they're attracted towards each other.
K, Q1, Q2 overall.
That's right. So this force is just, literally, it's just like gravity. All right. We get, instead of G, capital G, we have a K, and we've got Q1, Q2 over R squared. Is how you calculate the force. We had mass with when we were talking about gravity. Here, Q is the equivalent of mass. All right, so they're identically. These are calculated the same way. So if we were to put some numbers onto this, I mean, how many charges do we got? Like 100 electrons worth. We're talking a lot of electrons here, right? Is it a coulomb's worth? How many electrons would it take to make a coulomb? Well, 1 over 1.6 times 10 to the minus 19th, right? That's a lot, like 10 to the 18th electrons worth. I mean, it wasn't a small amount of electrons. I'm not sure if it was a full coulomb, but it was probably maybe a percentage of a coulomb at least, a measurable percentage that I had transferred to the balloon. So we had a certain amount of charge here, and let's just say that that charge here forced, I don't know, a percentage of it over there, and that would and we have Q, so we'll call this one over here Q1, and this one over here is our Q2. And it doesn't matter which side you're coming from. It's like mass 1, mass 2. It doesn't matter if I reverse the order of the Q1 and Q2 in here, but you reverse. Multiplication is commutative, and we still get the same force, right? Newton's third law. So these forces are going to be equal and opposite, and just toss it in that equation, you get the answer. And Q is, K, they give you in here is what? It's called what? The Coulomb's constant, and it's 8.99 times 10 to the 9th. And then you can look at, the question is, what units is that going to be? Well, it's going to be whatever units it is that I need to balance out to make this newtons over on this side. All right? So our value K is 8.99 times 10 to the 9th. Notice this is, in our gravitational, our capital G was what? 6.67 times 10 to the negative 11th. And our units were such that it canceled out all the units over here to leave me with newtons over this side. So we're going to have newtons over there. We're going to have to divide by coulombs twice. We're going to have to multiply by meters twice. And so those are the units for that. And same thing for gravity. We would have to have newtons, and we're going to have to cancel out our masses, kilograms squared, over our and so we have mass we have meters squared over kilograms squared. Use this equation the same way. The only minor difference is our Q's, unlike masses, which are unsigned quantities, our charges are positive and or negative. So if we have a positive and positive, what are we going to get for our force? We're going to get positive, and that's going to be repulsive. All right. If we have a negative and negative, that's going to equal positive. It's still going to be repelling. If we have a plus or a minus plus, those two are going to be negative, so that means they're going to be attracting each other. That's an attractive force. All right. And it's pretty easy to figure that out because you know opposite charges attract. So to do these calculations, just when you review your gravity calculations of two objects or more, it's the same thing. You can do the same exact problems using charge. In fact, let's just take a look real quick. If we go back, just to show you what I mean in terms of the types of problems you could see with us. So you want to go back to the gravity work that we did back in January. that relate to Chapter 4 and look at these problems. These are some of the starter problems we did. And then we did some web assigns. Because I could turn every single one of those problems into an electric charge problem. All right. So here charge 1, charge 2 with a radial in between them. All right. And I could do these calculations. And well, I'm not looking for my weight on Earth, but this would be one charge attracting the other. How hard is it pulled against the other? But these type of problems are classic problems. If I have 3 charges in a line, what's my net force acting on the middle one? Is the middle one going to the left, right? And you could also so you can figure out the total force on it. And by the way, if you're talking about, if they give you the mass of the object, you could actually figure out how it's going to accelerate as well. If it's truly an electron, you could actually look at, if you're wanted to see how fast an electron would accelerate coming next to a negatively charged object or positively charged object, you can look up the mass of an electron, which is 9.11 times 10 to the minus 31 kilograms, I think. And you could actually use the mass, once you figure out the force, and figure out how fast it would accelerate in. And that's what you do when you're making a particle accelerator. You say, all right, let's make this charge differential and put an electron or a proton in there, and it'll accelerate across that gap. And we can actually calculate what that acceleration should be, which is to get up to a certain speed so we can have it collide with something to do some damage and split apart an atom or something like that. And that's all we're doing is using these calculations to figure out the force. We can figure out the mass of the particle that we're accelerating, and we can do all sorts of calculations. Standard equations, we've already done this with gravity, so we can do it with charge in the same exact way. All right, and remember, when we're doing it with 3 objects in a triangular setup, you're going to have interactions between all 3 objects that you'd have to take into account. For gravity, they're all attractive. For charges, some will be attractive, some will be repulsive, and all you'd have to do is add the components together just like we did before. Break them down into components, do each one separately, break them down to components, add all the things that are aligned, positive and negative, offset each other, and you get results. All right, so these types of calculations are pretty easy to do. It's just like gravity calculations. We're just using electric charges instead. All right, so that's forces. And if you look on page 504, they give you one of these triangular type of setups, just like we did with gravity already. All right. Now, let's talk about gravity again for a second. One day over on the board to the right over here, I talked about if you're sitting on Earth, if you're standing on Earth, what's gravity like on Earth? Is gravity uniform? Does it change? If I have a ball 5 feet above the ground versus 100 feet above the ground versus a mile above the ground, does it matter? No. So gravity on Earth is uniform, all right? And so, and if we were to take a mass, some test mass, we'll call this, and let it go, which way would it travel? Down. And that tells us the direction of the gravity field, okay? And because it's uniform, we could represent it like this, as uniformly separated arrows, and these arrows would be our field lines, all right? So we call these field lines. These are gravity field, F-I-E-L-D. All right, and the uniform separation of these show that we have a uniform gravitational field. If I were to go let's say, to Jupiter, what would Jupiter look like? Assuming you stand on Jupiter. What would Jupiter look like? I have my test mass. It would still drop down, but Jupiter has what? More or less gravitational attraction than the Earth would. A lot more, right? And so what would I draw for my lines here? A lot closer together. All right. All right. So the spacing of these indicates the closer their space, the stronger it is. The further their space, the weaker it is. All right. Now, in reality, on Earth is not this big flat field we're standing on, so we get this nice uniform electric gravitational field. Earth is a sphere. So my question is, if we were to zoom in on the sphere, if we were to take a little close-up picture, then we'd get that. All right. But what happens if we zoom out? What do these lines look like? They're pointed towards the center. All right. And I probably shouldn't have tried to draw so many, but it'll take me forever here. Okay, sort of uniformly distributed. Not quite, but let's spread these out a little bit. All right, close enough. So these are uniformly spread around the surface of the Earth. So like these are uniformly spread on top. But as you move away from the Earth, what's happening? All right, they spread apart. Right. So they're spreading here. In fact, as I go out, what happens? The strength of this field which is measured by how the spacing of these weakened by what factor? 1/r². All right. So, all right, there's our inverse squared relationship. All right. So that's gravity fields. And how do we measure how strong this gravity field is? Somebody tell me right now. I want to know exactly how strong Earth's gravity field is. What would you tell me? You give me a number. What number would you give me? Mm-hmm. Use it all the time. You'd say that G equals 9.8 meters per second squared. That's what you'd tell me. You'd tell me how strong gravity. Which comes from, if we take an object, it's going to accelerate, right? So we take the force acting on that due to gravity, divide it by the mass, get the acceleration, which is mg divided by g, and we get g. Everybody agree with that?
Wait, what? mg divided by g?
Yeah, so we take the force due to gravity, which is mass times gravity. I'm sorry, and we divide it by m,
Yeah.
and we get g, which is 9.8 meters per second squared. And the units are meters per second squared. Or we could say the units are, what, newtons per kilogram, right? 9.80 newtons per kilogram, which means we call this a test mass, all right? All right? If I take a 1 kilogram test mass and put it in Earth's gravitational field, all right, I'm going to get 9.8 newtons acting on that 1 kilogram. That's what this means. And there's 9.8 newtons acting for every kilogram of mass that I have. All right. On Jupiter, I don't know. Maybe it's 50 newtons per kilogram, which would mean what? For every kilogram mass I put over there, I'd have 50 newtons of force acting on. That tells us how strong the field is. All right, in newtons per kilogram. All right. So let's compare this to charges. Let me just write in a different color on here and compare this to charges. Let me start on a different page. So if I were to take a plate, and this would be like by the way, what we call a capacitor. Now this capacitor, if I were to take this side of the capacitor and using induction or conduction, cause this to be negatively charged, okay? If I had another plate right above it, and if I were to use induction, well, actually, if I make this negatively charged, and I put this across this one, I can actually use induction to do what? It'll force it. If this is all negatives here, and I bring this plate close to it, if this is metal, and I have a bunch of negatives and positives here, what are the negatives going to do? They're going flying, right? They're going to leave. All right, and what I'll do is, what I'll end up here is, through induction, I can actually induce these negative charges to flow away, and so all these negatives said adios, and they moved away. All right. What's left here, in between, is what we call an electric field. All right, just like a gravitational field, I have an electric field, and if I were to put a test not a test mass, but a test charge in there. And we start with a positive test charge as a standard, and that will tell me the direction of the field, okay? So if I were to put a positive test charge in here, which direction is it going to go?
Downward.
You say up, you say down.
No, I'm going to down. I want to go
Charges attract if they are opposites and repel if they're the same. So if we were to take this one test charge, put it in the middle here, it's going to go flying downward, all right? And that shows us the direction of our field. Our electric field is downward. And because these are uniformly distributed across here, we get this nice uniform field across here. And this is what we call an electric field. Instead of a gravitational field, we have an electric field. All right? Like before, our gravitational field is measured in newtons per kilogram. All right? What do you think this electric field is going to be measured in? Well, how many newtons of force are going to be acting on? Because we went from mass, we're talking about gravity, to charge when we're talking about electric field. So we have newtons per coulomb. All right. I'm sorry, it's supposed to be newtons per coulomb, which are charge units. Did you say that? Is that what you said? Newtons per coulomb? Who said that? Did you say newtons per coulomb? You predict that? Yeah. Did you look ahead and cheat? No. All right, 2 bonus points. We'll give you guys some bonus points. Did anybody else have bonus points? Who had clever ideas so far? Who got the can moving in the right direction? 2 bonus points for you. Write that out.
Still gets 2. Still 2.
Okay, I'll take 2.
Stop complaining before I turn into Pico bonus points. All right, 2 bonus points.
I put the balloon up on the wall.
You put the balloon up on the wall.
Do an experiment to tell mine.
We'll get you some bonus points here. All right. Now, let me ask you here. What if I were to take a solid metal sphere, all right, and no charge on it yet, but I have, so I've got, positives and negatives in balance here. Okay. What if I were to take these charges, and let's say I'm going to, either through induction or conduction, I were to dump a bunch of extra negative charges on here. All right, let's say I have, I don't know, double the amount of negative charges on this sphere. All right. Let me ask you, how much of those charges will be in the center of the object? Because they're going to distribute it evenly throughout the sphere. True. Yeah. So some will be like right in the middle of the sphere. Some will be like a centimeter out. I don't know. Let's say this. Some will be over here. Some will be over here. Some will be here. Some will be here. Some will be on this edge. Some will be on that edge. Some of that edge. Some of that edge. True. So all these excess negatives will distribute out throughout the sphere, right? So they're evenly spaced. Think about this. There's your 2 bonus points. All right. Now this is a conductor. They're going to fly the farthest apart they can get from each other. All right. So they're going to go all the way to the outside. All right. So let's make it a hollow sphere now. All right. Hollow metal sphere. If you were to have a big one, you were to step inside the sphere, open the door, step inside of it, and if lightning were to strike that sphere, and you were leaning up against the side, you had your tongue against the sphere when this happened, you were looking at it to see what it tasted like, and at that point in time, unfortunately, the lightning strikes it, what's going to happen to you? I don't know. What happens to you? Who's been in the Museum of Science? The charge is they will not want to go inside the sphere. They're going to try to they're trying to get away from each other on the exterior because going in is getting closer to each other. Going out is getting further away. None of them will be going in. All right? They're all going to be spread out uniformly on the outer shell of this, trying to find a way off and get away from each other. Now, I don't know how you're going to open the door to get out of there and touch the side. That's another problem, right? But the safest place to be in a lightning storm is where? Well, inside a building, first of all, right? but it's in your car, not because it has rubber wheels, but because you're in a metal body, and that metal body is basically a metal can around you, and so if you were to get struck by lightning, for the most part, because you have glass and stuff that you could conduct through it, so there could be some issues, but still, it's better than being outside. That electricity is going to be conducted through the outer surface of that, and it won't go to the inner portion of it because it's getting closer to each other, and they want to get it further away. And electrons, this is really closely related. Remember, electricity and magnets are two sides of the same coin. All right, they are closely interreactive, and we've seen on our little electromagnet, our little rare earth magnets, how strong the magnetic force is. Well, that's the flip side of that is the electric force. And I'm telling you, this is a really strong force. You saw it with a little bit of charge put in this. I was able to roll this can pretty easily. So these are very, very strong forces, very, very strong repulsive forces and attractive forces. And so these will make sure that they're not going to go in the center of this. They'll be on the edge. All right. So that's a good thing to remember. All right. All right. So now let's say then that I were to bleed off some extra negative charge. So I'm going to leave this positive, and let's say I were to take, I don't know, let's put a negative. I get one over here, a sphere over here that's going to be net negative. My question is, and this one you might want to try drawing on a piece of paper here. My question is, how could you map out what the electric field lines look like for a situation like this? And by the way, we can calculate the forces acting between these two spheres, for example. But let's say these spheres are stuck on two poles, the two insulators that are stuck over here. So I have a big amount of positive charge, this one, big amount of negative charge in here. And I want to see what the map out in 3 dimensions. I'm going to do it in 2 dimensions here, but in 3 dimensions, what our electric field map would look like. Well, what do I do to map out electric field? I insert into this a what? Test charge. Where do you want to start by putting it? Right in the middle. So if I were to put a test charge here, where does it want to go? To the left, all right? So I'll draw a field in black. So we've got an electric field going from here to here, all right? What if I were to put a test charge over here? What's it going to look like? And a test charge is always use a positive test charge sphere that the field looks like, all right? So over here, it's going to repel. So over this side, it's going to repel. How about over on the far side of this object? What's it going to look like? If I put my test charge over here, it's going to go to the right, all right? All right. Well, all right, so let's put it in a different location now. How about if I put a test charge, I don't know, up here? Well, it's going to be repelled away from here, but pulled towards there, but right in the middle. So this is getting a downward pull here, but a push away here. So the negative portion of this will cancel out with a positive vertical portion of that, and I'll be left with only the leftward portion of both, right? So I'm still, at this point, I'm going straight to the left. All right. My question though is, what if I put a charge over here? Well, let's put a charge like over here. Now I'm closer to this one, further to this one. So now we're going to it's trying to be pushed away from here, but I've got a stronger pull here, right? And it gets significantly stronger really quick because we got this 1 over r squared relationship. If I have the distance to an object, I quadruple my force acting on it, all right? And if I double the distance here, I just drop that by 1/4. And so this changes pretty quick. And so here I've got a direction that's going to be down in that way, and it's stronger too. So we can draw a longer arrow if we wanted to show that's a stronger force. What about up further? What about up here? We'll have a similar situation, right? But it's not going to be as strong a field. It's going to be a smaller strength, right? We've got the biggest strength here, smaller, and it's a 1 over r squared, which gets smaller and smaller. And if I were to do charge up here, it's going to be pulling down that way and not so much away from that, but it'll be pushed that way a little bit and pulled away further. But what's going to happen here, if you connect all these arrows, you get a pattern that looks like this. All right. So there's your electric field. And this tells you if I were to put a charge here, the force action is going to be a positive test charge would be pushing in that direction. If I put it right here, it'd be pushing in that direction. If I put it right here, it'd be pushing in that direction. Put it right here, it'd be pushing in that direction. All right. So this will show you the directions that a positive charge would move if you put it at that point. And it, since there's a force action, it'd be accelerating as well. So if you knew the mass, you could calculate the acceleration. And then once I have this field, I can say, all right, what about if I put a negative charge? If I put a negative charge right here, instead of moving this way, it'll move that way. All right. So negative charges move the opposite direction of the positive charge do. But to draw an electric field, start with a positive test charge, and which way would that positive test move, and that maps out the field. You can do a similar situation for all negatives or all positives. All right, let's just call it a different picture here. And then you can do all sorts of crazy combinations. All right, like all positives and positive, negative, negatives. Then you can start mixing up, like what if I put negative, negative, positive, positive, four things and compare them, and you get some really nice pattern. So what if I put a positive charge right here?
Wouldn't it stay there?
Yeah, I mean, if these are equal charges here, where I'm right in the middle, there's nothing here. So I've got nothing in between here. All right. Yeah. So what if I put up a test charge over here? I'm going to get pulled to the right. What if I put a test charge over here? I'm going to get pulled to the left. What if I put a test charge right here? Well, this one's going to pull. I'm going to pull a lot this way, a little this way. So I'm going to have something that's coming down in more so this direction than that direction. All right. Same thing over here. This is going to be symmetric. I'm going to have something like this. All right. What about if I had something like over here? A lot more this way than it would be that way. So I'm going to be a lot more towards the center of this, but then tilted maybe a little bit up towards that other one. All right. And the same thing over here. So what's going to happen is you're going to get these field lines that are going to wrap around like this. And up this axis of symmetry, you'll have no force action if you put it anywhere along here. So you'll get a field pattern that looks something like this. And for a positive, what would happen? What if I put my test charge right in the middle here? What's going to happen here? This is trying to be pushed this way and pushed this way. This one's trying to be pulled this way and pulled that way. All right. So it's sort of an equilibrium here. Which one's more stable? The ones being pushed on both sides, or the ones being pulled on both sides? This is sort of like pushing down on a watermelon seed, right? This thing's going to go squirt someplace probably, right? So this is an equilibrium, but a very precarious equilibrium. This is an equilibrium where it's just getting pulled on both sides, and this is a little bit more. This is like stable and unstable. So there are different types of equilibriums where you're stable or not stable. This one, you disturb it a little bit, it's going to go flying off because it's trying to get pushed by both of these. So this one is trying to get. It's getting pushed this way, and it's getting pushed this way, but with big forces. And so something weird is happening there. What if I put my positive test charge over here? It's going to go to the left. All right, so we've got pushing out to the left. Same thing there. What if I put a positive test charge here? I mean, this is going to be pushing it this way, and this one's going to push it a little bit more that way. So, yeah, we're going to be something out like this. So we're going to end up something that goes like this. So it'll be the opposite type of diagram. All right. And then you can do weird patterns where I could take like three or four or five objects, and you can do the same types of things. All right. But those are electric field patterns. All right. And you can see, and that's 15 force per unit charge. All right. We drew electric field lines. That's 15.5. And you can read about the last couple of sections are a couple of applications. You can skim through that. The calculations are just like gravity. So if you know how to do gravity calculations, I'd practice a few of these problems. and you'll see they're identical types of ideas. All right. They don't do capacitance, so I'm skipping 16. Chapter 17. All right.